Hi everyone, thank you for being here. Today, my name is Burcu, Güldür, Erkal, so I'm from Technical University of Applied Sciences, Augsburg. Today I'll be talking about determining the risk conditions of structures through 3D modeling. This is actually something that we were curious about, so it's not an extended research project, but we were curious about something with my colleague from Hacettepe University, so we tried to look at it. So, basic outline, research motivation, methodology, data set, 3D models, and results I'm going to go through. But let's start with the motivation. So nowadays we have many types of sensors, very accurate data processing or collecting techniques. You can see photogrammetry, laser scanning, synthetic aperture radar. So for developing countries per se, it is not always the case that you have access to those data or you have opportunities to perform this in a large setup, right? So in Turkey, we finished up a project for one city, which we're trying to, so we worked with ministry, and we were trying to find out the seismic probability risk of the buildings, there's only buildings. And it took us nearly 2.5 years to go through, I think, a really small portion of the city. So we were trying to see, okay, so this takes a lot of time and we don't have the resources. Can we help the ministry, using a very simplest way to use the Google Street View to give some sort of idea about like anything that we can get from these data sets. So as it is very well-founded and very applicable at this point, you can get the images, create the point cloud. The resolution is bad, obviously, in this sense, but then you can generate a 3D, texture mapped 3D model. So, saying that, we wanted to see earthquake-prone regions, so they're like really small cities, and this is one of the cities where the 2023 Kahramanmaraş earthquake hit. So it's Nurdagı, it's the base of it, so like the epicenter of the entire event. So as the traditional surveys are time-consuming and costly, so these are the images before the earthquake. So we were trying to see if we were able to get some sense of quick information. So we just get the Google Street View imagery, pre-hazard 3D modeling. So we selected Nurdagı region and tried to see if we can actually get some information. So this is all messed up at this point, but the tool, Python, Structure for Motion, Meshroom, and Meshlab, so we just use the available software, open source softwares that we can find, and we did image matching, so it's all on the wrong direction, but image matching, feature detection, object creation and motion, and then we go all the way to the 3D model after the texture mapping, so to give us a sense of the 3D model for the buildings. So what we did is we just put, like a man, and then it's just gonna move around and get 360 images and collect, and then from the 5 perspectives, can we get the model of the entire building? So that was the main image. So as you can see, so there's like, we collected the data with certain intervals, and in order to enhance the depth perception of the model, so we try to make sure that we have at least 5 perspectives for each building. And so we performed the camera calibration and feature extraction, image matching. As I said, we use structure for motion, depth map, surface match, and texture mapping. So all in all, we had, as you can see, very bad resolution models. But in sense of understanding, so as I said, let me go over the software one more time, but I don't want to focus on those, but Meshroom is the SFM software, and the Meshlab is something that you can use to play with your point cloud, basically. So here is the 3D model, a couple of buildings. So we did it for 170, but this is only just 6 of them. But what we were trying to get is actually, I wanted to focus on this part. So I'm a structural engineer, so I would like to know a couple of things about the buildings, right? So building age is one thing that I can look for when I'm trying to get the seismic risk pronity, so for these structures. Number of stories, regularity, structural system, architectural irregularities, condition of materials, ground floor usage, and site conditions. So a couple of them I can get, right? So a couple of them are already in the municipality. like the building age, structural system, so that I can get those information, but the couple of things that I can get easily from the images that we collected. So we could have done this from the images as well, but it's very easy when you get these models, obviously. So the number of stories, architectural irregularities, and the ground floor usage. So especially the ground floor usage is very important for us in Turkey because it is not allowed. But in small towns, small regions, it is very common to cut down the columns to create large spaces. And they do it for the bottom 2 floors, generally. So that creates a huge problem for the earthquake-prone regions. So that's one of the things that we want to detect. So as you can see, for these 6 buildings, I don't want to give everything, but just for these 6 buildings, so number of stories are actually, the last example was a little bit rigged. I can show it to you. So the problem is here. So the bottom portion, so it's only selected as the 1 story because what we did was try to look at the windows when we were detecting, so the story number. But since that didn't have those windows which are extending all the way to the down, so it was not able to detect that, so that was it. But all in all, number of stories was not a problem because it was easy to detect that information. Overhang was not a problem. As you can see from here, like if you have, actually I'm looking for a good example. Sorry. So here actually, maybe you can see it, but this has an overhang. So every single building had it. Actually, it was again very common in Turkey to have the first floor a little bit smaller than the rest of the building. So you can actually get the overhang quite easily as well. So, and then irregular floors, as you can see, since the point clouds were not complete. So the irregularity was a little bit of a problem for our detection process, but this is how I defined it. Because, like, you know, since I had the irregular floor, so the floor plan is changing. Since I don't have the complete point cloud, that was the reason that we couldn't get that information. So the ground floor usage, which was very important for us, so the 4 of them was okay, but the last 2, as you can see, were not detected. Actually, as you can see, these are stores right here, larger story height. But the reason it was not detecting again is because how we set up the detection was to, we search for some information regarding the store itself, like a writing or a picture or something when we were detecting this. So if it didn't have that, then we said, okay, it's a regular story. So the reason that we couldn't get the last 2 were because of that. But if you change your detection algorithms, obviously, it will improve. Anyway, so these are the things that we wanted to explore a little bit. This can obviously be improved by using different sensors, different data sets, but all in all, it is easy enough to create this kind of pipeline to get some initial information and guide at least the people in the municipality to focus on which parts of the city first and then go from there. So it's like a improved process for their side. So there are limitations, obviously, but the workflow has a strong potential all in all. So the occlusions, always a problem. Partial views reduce our accuracy, as I said, so we cannot always match it up with other sensors. And automation of feature detection, improving our detection strategy, and integrating with GIS maps will be something that is useful for, again, informing the related parties. So these are the references, and thank you for listening.